Okay, morning. Let's continue on the Fourier series, and we'll start Fourier transform today. Okay, hopefully. Okay, before we start, just want to show you this picture right here. Okay, this is the Eiffel Tower, actually, part of the Eiffel Tower. Now, if you look in the middle of the tower here, there are 72 names engraved on the Eiffel Tower. Okay. There are 72 French scientists, mathematicians, and engineers. There are a lot of the names that's actually familiar to us, like Lagrange, Laplace. Right? It was a truly amazing period of time. France produced so many famous mathematicians, scientists, and engineers. Okay. So if you've ever been there, try to find your favorite Laplace or Fourier. Okay, let's continue on the Fourier series. Okay, in the previous lecture, I talked about the Fourier series in different formats. Okay, one format is the trigonometric type of format. Okay, the other is the compact form, and the last one is the so-called complex form. So for complex form, f of t is written as this is the complex form for the Laplace transform, Laplace Fourier, a complex form for the Fourier series. Okay. Dn at here is equal to an minus jbn over 2, which is also equal to 1 over t naught, 0 to t naught, f of t e to the power negative gn omega naught t dt. And d naught, when n equal to 0, d naught equal to a naught. Okay. So that's the complex form, and the connection between complex form and the trigonometric form. Okay. Now, first of all, you have to a few comments here. So the dn at here, okay, is a complex number. In general, it's a complex number, but I'll show you an example, a very special case, and this actually could be just a real number. Okay. Now, because this is a complex, so this needs to be complex somehow, then you end up with a real function, right? And you can calculate the magnitude of a dn to give you the so-called amplitude spectrum. Okay. Now the other thing is, if you look at this formula, okay, it goes from negative infinite to positive infinite. So when n is negative infinite, so you basically get the dn and the d negative n. Okay. So when n is negative value, then you get a d negative n, right? Okay. So if you do this, this gives you amplitude spectrum. And if you calculate the angle associated with this complex number, then you get the phase spectrum. And these two together, you get the so-called frequency spectrum, right? So sometimes we call this as an exponential frequency spectrum. So these two spectrum together, you get a frequency spectrum. Okay. Actually, sorry, exponential Fourier spectrum. Okay. So I'm not going to plot this at here. So I'll show you an example how to get this dn out of this formula, okay, given a periodic function of f. Okay. So then that should be okay. Okay, so by the way, I'm going to update the formula sheet a little bit to include just a little bit more, a couple formulas for the Fourier series. Okay, yeah, and we'll use the updated one for our final exam. Okay, let's say we have a periodic function, which is a rectangular box at here. Okay, so let's say this is the f of t. Okay, amplitude here, the box has an amplitude of a at here. Okay, so I need to calculate the Fourier series. So let's find the Fourier series in the complex form. Okay, for this periodic function. So this definitely has a period of t, right? So t naught at here is t. So if you look at, doesn't matter how you count it. If you start from here, and that's one period. If you start from 0, that's also one period up to this. Okay. So the period of this function f of t is t naught is t. And now we're trying to calculate the coefficient dn at here. Okay, so this dn. So dn has this formula, and d naught is basically an. So if you recall, an, right, is 1 over t naught and 0 to t naught, and f of t and e. And it's just dt, right? Yeah. So let's do all of the calculations that are here. Okay. Now I'm going to show you this one later. Okay. Here. A little more space. Okay, first d naught. Okay, so d naught is 1 over t naught, 0 to t naught, f of t dt. Okay. T naught is t, so 1 over t. Now the integration at here, if you recall that, okay, even though the formula you can do from 0 to t naught, which is t at here, but you could actually integrate any intervals as long as the interval is a period of a t naught, or t in this case. So I will choose to integrate from here to here, okay, instead of from here to here. Okay. It's the same thing basically, okay. But it's a little easier to integrate from here to here, okay. Because I know for sure when I integrate from here to here, right, I know I'm just only need to integrate from negative d over 2 to positive d over 2, because that's where you have a non-zero value for f of t. And with then negative t over 2 to positive d over 2, the function f takes a value of a, and this will give us a d over t. Okay, so that's d naught value. Okay, and then dn. Okay, so dn formula for dn is 1 over t naught. Okay, similarly 0 to t naught f of t e negative j n omega naught t. Okay. Always remember omega naught is 2 pi over t naught. So instead of integrating from 0 to t naught, we're going to integrate the same thing from negative t over 2 to positive t over 2. And within this interval, right, we only need to integrate from negative d over 2 to positive d over 2. I noticed sometimes my OneNote, all of a sudden some of the writings disappear. Yeah, this is so that's kind of annoying. So when you look at my in-lecture notes, okay, if you notice anything disappear, it's not because I intentionally erased them, okay? Okay, so what do we need to integrate? We only need integrating from d over 2, negative d over 2 to positive d over 2. Within that interval, the value of the function is a. Okay. So for this integral, it's not a very difficult integral. It's actually a simple one. But you don't have to be confused. Now you do see the j at here, n and omega naught. So, but you're really just integrating with respect to t. Everything else is considered as a constant. Okay. So this is essentially just exponential function and integrate about it. Okay. So now I can take the a out. Okay. And the integral of the exponential, okay, is 1 over negative jn omega naught at here, and then this is basically the results of this integral. Plug in the limits, okay, like that. Once you plug the limits for the t and also simplify it, you can simplify this complex number. Instead of a g at the bottom here, you multiply the g at the bottom and the amount of g at the top, right, to move the g to the top. Okay? So I want you to simplify yourself here. Okay? So once you do that, the results of this is actually turned out to be a real number instead of a complex number. So the results of this the limit, once you plug in the limits and simplify it, and you get this as the results at here. So amazingly, it's actually real. So the dn at here is always a real. That's a very special case. And so dn in general should be a complex. Okay, yes. Oh, she. Why does it happen all the time? Anyway, you know what I'm writing here. Sorry, what's the question? Yeah.
1 over negative j and omega naught. Is there a t at the end of that? Or is there
no t, because this is the integration, right? It's like integral of negative at dt. So you end up what? Negative a at the bottom. This is the integration results. Right. Okay. Yeah. Okay. So. All right, I'm sure there's. Okay. Okay, so that's what you get for the dn at here, okay? Yeah. So when you plot this dn, I'll show you what this looks like. So you can plot this dn, okay? Plot both its magnitude and the phase angle associated with the dn. So here's dn here, right? This is a dn. If we can do this. Let's say we let d over 2 equal to 1, and a equal to 1, and t equal to 8. So we can use some numbers at here. If I plug in d over 2 as 1, or d equal to 2, capital T equal to 8, and capital A equal to 1, then we can calculate the magnitude of this, right? So the magnitude of this, basically whenever you plug an n number into this, then you get a magnitude. Okay, we take the absolute value, we plot it, so this is what you get for the absolute value of this under that set of values. Okay. What about the phase? This one is a real number, right? So what's the phase of a real number? For example, when I say, what's the phase for number 3? 0, exactly, right? Phase, basically, you still think of it from your complex plane. Okay, excellent. So if this is a real plane, this is an imaginary plane. Whenever you have a complex number, this is the phase, right? This is the phase of theta. So if you have a real number, this is the location of that number. So the phi value is 0, right? Now for this dn, calculated dn here, if you look at this one, if you plug this d, small d, capital A, capital T, the sign of this number is determined by what? By the sign, right? As the angle changes, the sign can be positive, can also be negative. So this number could be a positive number, could be a negative number. Okay? All depends on the value of the sign as n is changing. Okay? So that's why you see here, you see a positive value, phi, negative pi value. So when this is a negative number, for example, if it's negative 3, and its phi angle associated with it is pi, right? When it's negative. When you have a negative number here, it's over here. And the phase angle associated with that number is 180 degrees. Okay. So that's why you see the variations of this angle between negative pi and positive pi. Okay. So that's how you plot these two things here. If you plot it using the complex form, okay, you'll get exactly the same thing, basically. Okay, okay, so that's an example to write a periodic function in terms of a complex form of a Fourier series. Okay. So basically, that's pretty much all about Fourier series now. Okay. So let's look at the last topic. Okay, I do have another one called basically the power theorem. I think I'm going to skip that one and make it as optional. Okay, so there's another topic. You take a look at the lecture notes. It's called the Parseval theorem. Okay, it's a very simple theorem. Basically, this gives you what's the power of a signal. If you have a signal given, then what is the power of the signal over certain amount of time. Okay, if the signal is a periodic function, then right there's a power. If non-periodic, you also have a power, right? So how do you calculate the power of this? It's given by this possible theorem. Okay, so I want you to take a quick look at this. It's a very straightforward theorem. Okay. The last topic is Fourier transform. The Fourier transform here. Now Fourier transform, I have different ways to cover it. Okay, there's a lengthy way which I did actually in the previous year. Okay, there is a not so lengthy way, but it's not so straightforward. Basically, just give you the formula. Okay, I think I'm going to go through the little bit lengthy way here, just to give you a little bit more background of how Fourier transform is derived. Okay. So let's consider f of t. Okay. In this case, the f of t is a aperiodic signal. Aperiodic basically is non-periodic. It's not a periodic function. Okay. So this is different now, right? So now the previous one, Fourier series, we deals with a periodic function. Now this time, we're considering an aperiodic signal. So if I plot it, okay, this maybe is what this f of t looks like. Okay. Okay. But I want to actually associate this aperiodic one, okay, with a periodic one, so that I can actually derive the results, okay, out of a periodic function. So this time, what do is, I'll do this. I'll make a copy of this f of t. Okay, so here is f of t at here, and then I'm going to copy it. Okay, and make it, okay, a periodic function. So if this is f of t, this single one is f of t here, and I'm going to make it a periodic function f called ft naught t. Okay, this is all we're doing here, right? We're making copies of it, and then we make a new periodic function out of that aperiodic function. So this is f of t naught at here. So f of t naught t, okay, is a periodic function or signal with t naught as the period. Okay? Yeah. So we can do that, right? We just take it out, put it there, right, and make a periodic function. Okay. But there's a connection between this periodic function and the original aperiodic function. So the connection is this. If we let's say we do this, if we let the t naught go to infinite, okay, if we let the t naught go to infinite, then what happens is the next bump, right, will go to the left or right, okay, infinitely further and further away. Okay. As t naught go to infinite, it's like you don't see this anymore, right? So then this basically becomes this f of t back to f of t naught, right? Yeah. Yes.
Would it also be the case for the ones in negative?
Yeah. So as t naught go to infinite, oh, this is happening again. Then the negative t naught becomes negative infinite, right? Yeah. So it's inherently over there. Okay, good. So this is the idea now, right? So if I construct a periodic function out of this f of t, and then I let the t naught go to infinite, then I will get back this f of t. So then the focus at here is I will make use of the Fourier series, okay, that I have learned, apply to this periodic function, and then at the end I will let the t naught go to infinite to obtain f of t. Okay, so that's the train of thought at here. Okay, yeah. So what is f t naught t? Right. So this one here, f t naught t, and f t naught t is a periodic function. So we can write that using this complex form. Okay. So we can write it using this complex form here. This is f t naught. Okay. And omega naught equal to 2 pi over the t naught, again as euro. Okay. And the dn, as we learned, right, as we also exercised, that's how you calculate the coefficient dn based on this periodic function. Okay, so you're integrating from negative t naught to t to t naught over t, half of t naught over t to positive half t naught over t. Okay, and then adding up this. Okay, so that's all we have learned. Okay, based on the previous lecture. Okay. So then what I'm going to do is this. I will substitute this one, okay, into this expression. This expression is the complex form for the Fourier series. Okay. So I'm going to substitute this one, okay, into this summation. So once we sum it into it, so f of t naught t, okay, and equal okay, so this is the dn, and then times ejn omega naught t. There. Okay, so in overall, this is what the periodic function, okay, looks like after you substituting it into it. So we do have a t naught over here. Okay, this t naught, right? And t naught, if you recall that, t naught is over here. It's 2 pi over omega naught, right? This is t naught. Then 1 over t naught is what? Omega naught over 2 pi. Okay? So I'm going to replace this 1 over t naught with omega naught 2 pi. This is a constant, so you can literally take the constant out of the summation sign, right? Because it's constant times everything else. So if you do that, okay, you get 1 over 2 pi outside at here, the summation sign, and then you got this integral in the middle. And you also have this term here. Okay, let's make a big bracket. And the outside is the omega naught at here. Okay, so I move the omega naught to the end of the expression now. Right, so this t naught, 1 over t naught is omega naught over 2 pi. omega naught over 2 pi is that one original term. So move the omega naught to the end of it. Okay, to the end of it. Okay. Okay. So from here, one more manipulation. Okay. So you look at the T naught, right? So what's T naught? T naught basically is 2 pi over 2 pi over T naught. Omega naught equal to 2 pi over T naught. Okay, keep manipulating this. And then as T naught go to infinite, then this omega naught goes to what? 0, right? Goes to 0. Okay. So basically, if you think dn, right? This dn, we typically do this. We plot absolute value of that. We also plot the angle of it versus what? N omega naught. Okay. So basically, at this frequency, at n equal to 1, 2 times this, 3 times this, what's the magnitude? What's the phase angle? Okay. Yeah. And between each one of the plot, right? If you look at this, between each one of the plot, the two bumps at here, the interval here is just omega naught, basically. Then as T naught go to infinite, the omega naught becomes smaller, smaller. So this interval at here will become what? Smaller and smaller, right? So the two bumps will become closer and closer to each other. So there will be basically more of these bars, right? And it's as if you got a sort of a continuous plot now, instead of this kind of discrete plot. So that's what happens when your T naught goes to infinite, basically. Okay? So this omega naught, right? This omega naught is like a and that's the Fourier series. And by the way, it's actually wrong, so I just want to show you, right? It's the importance of learning math. Omega naught, I can think of it as a delta omega. Okay? Yeah. Because basically, the interval between this is omega naught. It's like a delta omega here, right? Delta omega. So I'm going to replace basically a couple of things within that formula. So here's what we're going to replace. We're going to replace omega naught with delta omega. Okay? Yeah. Then as T naught go to infinite, the delta omega becomes a differential omega. Right? So delta becomes a differential sign. So basically as T go to infinite, this term I will replace that with delta omega, and then it'll become differential omega. Okay. And also the n omega naught. Okay, the n omega naught becomes n delta omega and becomes basically omega. Okay. So when you have let's say 3 times delta omega, for example, over here, 1 times delta omega, this is omega. 3 times omega, this is omega up to this. So n times delta omega is always the frequency value at the location n. Okay. And with this substitution, okay, so this function over here, okay, as T naught go to infinite, and that function becomes, so f of T naught t becomes f of t, and then this f of t can be written as, much cleaner writing now, okay. So now we have a new expression for the f of t, and based on the approximation from a periodic function. Okay. Oh, it happens again. There. Okay. So this is your f of t. And what's inside this, right? The internal integral at here, this internal integral, we define it as f of omega equal to f of t ej omega t and dt. Okay. So I guess I could use t at here actually. Sorry, I should use the t at here. I use a t. Okay. There. Okay. So what we have, this one here is the so-called Fourier transform. Okay. This is basically Fourier transform. So what this Fourier transform is doing essentially, if you look at it, it's a transform, right? Try to relate to the Laplace transform, and that's probably the only kind of transform you have learned so far. So you're transforming a time domain f of t into omega domain, which is a frequency in this case. So you transform a time function into a frequency function omega. So sometimes this side here is also written as could also be written as f of j omega. Okay. F of j omega. Remember what Laplace transform is. Laplace transform is what? E to the power of here is, what's this? S, right? Of this. That's Laplace. So the only difference between this, you're doing transform here. See here, this is j omega, this is s, but this is negative infinite, this is 0. Okay? So basically, I could do this. If I remember what the s is. S is sigma plus j omega. It's a complex number. So I could let sigma equal to 0. Then also at the same time, relax the limit, okay, from 0 to infinite to negative infinite to positive infinite. Then we get the Fourier transform, basically. Okay? Yeah. But there's a lot of differences, though. Okay, between the Laplace, there are a lot of similarity, but there are differences. Okay, I think I'll point it out later. Okay, so this is essentially the Fourier transform. Did you see the mistake here? Yeah. Either you have 2 pi. Or either you don't have 2 pi. If you use 2 pi, it's not omega, it should be what? The frequency f. So omega equal to 2 pi times f. Okay. Oh. If you ever want a tattoo, make sure you got it right? Yeah. Anyway, so what do we use the Fourier transform for, right? I know this is the last lecture, so I typically don't have very high expectation for this topic at here. You will learn more in your future lessons, especially if you're going to electrical program. Okay. But the Fourier transform, focus on this formula here. Okay. Focus on the formula f of omega equal to negative infinite to positive infinite e negative j omega t and dt. Okay. So I think this is what you need to focus on at here. Okay. So this is the transform from f of t to f of omega here is t domain, here is omega domain or frequency domain. Okay. So that's the first impression you should have. And f of omega, by nature, it's complex number. Okay, so it's complex number by nature. As long as it's complex number, then you can always write this complex number through its magnitude and its phase angle. Right? This is basically the Euler's formula. Okay, you can always write a complex number. Right? Whenever you have a complex number here, you have a magnitude, you have an angle theta or phi. So you can always write it as r times ej theta. Right? That's complex number. So this f of omega that you obtained here is a function can decompose into two parts. One is this, let's call this is amplitude. And then the other is phi, this is the phase. Okay. With the transformation from t domain to the omega domain, so you got two new information hiding behind this time signal. What are the information? One is the amplitude, the other is the phase versus omega. So both of this can be plotted, right, versus of omega. Very much like the periodic function, right? Periodic function, you can do the same. You plot the magnitude and phase, okay, behind this periodic function. And same thing, you can plot this behind the periodic function. Okay. Yeah. So Fourier series, that's why a lot of time Fourier series is very useful in signal processing and also including basically image processing. Okay, so you can use it in signal or image processing. Okay. I showed you the Laplace here. You notice the similarity between Laplace and the Fourier, but Laplace often is used in control applications. So that's what Laplace typically used for. If you're designing a control system and you want to design a really good control system, right? And you want to study the system to have a better idea, and use Laplace to basically transform original, for example, system model from time domain into S domain, and then you study it within the S domain, and you design your controller also within the S domain. Okay, and then you can get back to look at the response in the time domain. Okay. So that Laplace is often used in control applications. So in your third year, when you're learning control system, and you'll see Laplace again, right, to study the control system. And when you're taking signal processing communication course for electrical student, then you'll see the Fourier transform in that course. Okay, yeah. And I'll show you also a different the differences actually through a couple examples. Okay, for Fourier transform and Laplace transform. Okay. So from here, next what we're going to do is very much Laplace. When we learn Laplace, and I showed you what's the typical, what's the Laplace transform of a typical function. You know, when you have a, let's say, unit step function, its Laplace is what? 1 over s. When you have an impulse function and its Laplace is equal to 1, right? Excellent. So we have studied, you have the table of that. Okay. So next we'll do very similarly. So what will be a Fourier transform of typical signals? Okay. And I'll show you a couple of things. Okay, yeah. So you can relax a little bit. For this part, we're still not quite deciding whether we're going to test it or not yet. For the Fourier transform, okay? Fourier series definitely will be tested. Fourier transform, I'm not too sure yet. I'll talk to the other instructor, and we'll send out the email just to let you know, okay? Yeah. Okay, so let's take a look at one Fourier transform. Number one, let's take a look at this one. What will be the Fourier transform of a shifted impulse function? Okay, what will be the Fourier transform shifted impulse function? I will use the formula to calculate the Fourier transform of this. The symbol-wise, we use this in a lot of textbook. This is a capital F, okay, indicating we're taking Fourier transform of this time function f of t. Plugging f of t into the formula. Here's f of t, and then negative e to the power negative j omega and dt. Okay. So once you plug it in and you look at the integrand, we apply the property of impulse function. Whatever function times impulse function shifted one, right? So then what happens is it exists only at t equal to t naught. So you can keep this as it is, but then the other exponential term becomes e to the power negative j omega t naught and dt. So I can take this term out of the integrand. You're left with just the integral of the impulse function. So when you integrate from negative infinity to positive infinity of this impulse function, this one equal to, what's it equal to? The area underneath the impulse function is always equal to 1, right? So you end up with just this, okay, just this. So this is the Fourier transform of the shifted impulse function, okay? Then what about the non-shifted? For example, let's say if t naught equal to 0. If t naught equal to 0, then we get the Fourier transform of delta t, which is 1, right? That's the same as what? The Laplace results, isn't it, right? Yeah. As a matter of fact, you look at this result set here. Okay, if you look at these results, if I ask you what is Laplace of the shifted one, which is what? The e to the power t naught, right? T naught. Okay. So if you replace s with j omega, you get the Fourier here. Okay. So that's a connection. But that this replacement doesn't. It's not true all the time. Okay. For some it's true, for some it's not. So between Laplace and Fourier, sometimes you can simply replace the s with j omega, then you get it. Okay. But not true all the time. Okay. So bottom line is, when you take the Fourier transform of the impulse, you get 1. So what's the significance set here? Now remember, I emphasized a lot in terms of the importance of the impulse signal. Impulse signal, if you give the impulse signal to a system, you get the impulse response, right? And impulse response is so important because if you have it, then you can convolute with any other response, any other input, then you get the new response. Okay? So this is actually wired here. You look at the Fourier transform of the impulse, you get 1. Basically means if I plot the absolute value of this for the impulse signal versus omega, guess what do I get? I get a constantly a 1 at here, right? Which basically means the delta t impulse signal literally has all of the frequencies in itself. So that's why impulse signal is a very powerful one. It has all of the signal. If you look at the spectrum in here, you look at the spectrum. Behind delta t, there is all the components for all of the different frequencies. So that's why impulse signal is so important. Unfortunately, you can't have it in real life, right? Because it contains all the frequencies. Okay? So I'll finish this a little bit, and then we'll use the rest of the time to do a quick review in Friday's lecture. Okay? Yeah.